Hello everyone, and welcome back to another video. I'm back from my vacation, which was very nice. Love Buc-ee's. But anyway, what we have here, since summer is almost coming to an end, I figured that I would finish off the Squircle series. So what we have is the kth dimensional Squircle, or at least the integral for it. And what we're going to be doing is going to be finding the volume, or could you call it like hypervolume or something? I'm not entirely sure. But we're going to be finding some sort of volume of the kth dimensional Squircle to kind of finish things off. So, let's get started, shall we? The first thing we're going to do, actually, is kind of justify the approach we're going to take by looking at the 2- and 3-dimensional counterparts, right? So, for 2 dimensions, we know that the integral is just this. We have the integral from 0 to r of r to the n minus x to the n, all to the 1 over n dx. And the way we would solve this is just say, well, just let, u equal x to the n over r to the n. And from that, we can just use use one of the beta function integrals, convert it to the gamma function, and then we're done. But for the 2-dimensional one, it was a little bit trickier, right? What we said is, so for the 2-dimensional one, 0 to r, and then we have 0 to r to the n minus x to the n to the 1 over n, and we had r to the n minus x to the n minus y to the n, all to the 1 over n dy dx. Now in this 3-dimensional one right here, what we did is, well, we did one substitution, say u equal y to the n, but then over r to the n minus x to the n. And then afterwards, we did another substitution, essentially the same as that one to finish it off. So the method we're going to be taking with this integral right here is essentially continuing this trend right here, continuing this trend of substitutions. And yes, this does mean a kth. So we have k many variables. It's going to be a k variable transformation. Meaning we're going to have a like a k by k Jacobian, which is kind of cool. But I'm getting there. I'm getting there. So what we're going to do to actually evaluate this integral is make the following substitution, which is u1 is going to be equal to x to the n, or xk minus 1 to the n, over r to the n minus x1 to the n minus ... x to the n, or xk minus 2 to the n, where everything in between is just everything leading up to that. And we can define u2 in a similar way, right? We can say u2 is equal to x to the n k minus 2 over r to the n minus x1 to the n minus ... minus x k minus 3 to the n. And what we can essentially do is just continue this trend. So ... up until uk minus 1, pardon me, is just equal to x1 to the n over r to the n. So with this trend in mind, we can notice quite a couple things about the following transformation. And the first thing I'm actually going to point out is that the relationship of, say, u1 to u2 and etc. So let's just take a look here of what we have. On the denominator, we have, r to the n minus x1 to the n ... But we can, you'll note, pardon me. You'll see we have this term right here, this x to the n, or xk minus 2 to the n. But you'll also see here that we have the same exact term in the numerator right there, and that there is something very similar in between. So let me just kind of write this out a little bit neater. We can say that xk minus 2 to the n is just equal to u2 times r to the n minus x1 to the n dot 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 xk minus 3 minus that, really. Because you just multiply both sides by that. But what we can do is just substitute this in, right? And this is our result. We have x, the numerator does not change. We have xk minus 1 to the n. But then in the denominator, you'll see that we now have, well, r to the n minus x1 to the n dot 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 minus xk minus 3 to the n. I'm writing it like this because we're substituting in the xk minus 2 to the n. So now this xk minus 2 is just, well, all this. So u2 and then r to the n minus x1 to the n dot dot dot. This should really be, okay. Ooh, let me scoot this over real fast. And then we have xk minus 3. And you'll see here that we can actually just, well, factor out that term right there because it is the same. So doing so, we find that this x to the n, k minus 1, u1 is equal to the numerator divided by, well, just 1 minus u2, and then r to the n minus, I'm just going to write dot 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 for the sake of brevity. But you'll see here that we can just have, according to this transformation, we can just have, say, an xk minus 3 right here, right? So the next one in this sequence, for example, the next one would be, say, u3, and that right there is equal to x to the k minus 3 to the n over r to the n minus x1 to the n dot 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 minus xk minus 4 to the n. But you'll see that we can just continue this trend. We can just solve for this right here, plug it back in, and what we'll get is just this continuous multiplication of these 1 minus u terms. So another way we can actually write u1 right here is just, well, x to the n, k minus 1, but then divided by 1 minus u2, but then 1, or times 1 minus u3, 1 minus u4, and this would just continue up until we have 1 minus uk minus 1. And we can express every single one of our u's as such. So, for example, scrolling on over, we see u2, which I'll just write in blue right here as well. u2 can actually just be defined as x to the k, xk minus 2 to the n over 1 minus u3, and then 1 minus u4, dot dot dot, and then 1 minus uk minus 1. And it might not seem immediately obvious why this relation is important, but I'm getting there. So now let's kind of just keep this in our back pocket and go on to the Jacobian. So we know that, for like single variable functions, if say you're doing like a u sub, right? What you need to find is du is equal to, some nonsense and then dx, right? And this nonsense right here is what we call, or in higher dimensions, I guess, this nonsense right here is what we would call the Jacobian, right? So this nonsense is actually just called j. In this notation, I suppose these would actually be like vectors of functions. And Jacobian is a matrix, but anyways, I digress with the details. The point is that we need to find dx, dx1, dx2, dx3, all those terms multiplied together in terms of du1, du2, du3, etc., all the way up to duk minus 1. So the way we're going to do that is construct our Jacobian, which is going to be the determinant of, well, one really big matrix. And what this matrix is all of our u's right here, so u1, u2, all the way up to uk minus 1, in each row. So, for example, this right here would be our column of u1, this right here would be column of u2, u3. And then each row, it's going to be differentiated by a certain variable. So kind of completing the matrix here, we're just going to have some dot, dot, dot. So dot, dot, dot. This is going to be uk minus 1. And on each row, what we're going to have is we're going to differentiate with respect to each variable. So on this row right here, we're going to differentiate with respect to xk minus 1, and then we're going to have xk minus 2, and then dot, 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 all the way down to x1 itself. So evaluating this matrix seems extremely daunting, especially because we're, taking its determinant, for goodness sake. But hold on a second, it's not as terrible as it seems. So let's just compute the first couple terms, right? What is u1? u1 right here is just, well, x to the n, k minus 1, and then we have the denominator, all that. So the derivative of that with respect to k minus 1 right here, well, that's just going to be, we just have to take the derivative of that top bit, which actually isn't too awful. You can do that, right? So what we have is just n xk minus 1 to the n minus 1 by the power rule, and then in the denominator, it remains just the rest of this. So r to the n minus x to the n minus dot, 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 x1 to the n, pardon me, minus dot, 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 xk minus 2 to the n. Okay, cool. Now, what is the derivative of u2 with respect to xk minus 1? Well, quick question. Do we see an xk minus 1 in u2? And the answer is no, but there is no xk minus 1 in u2. Thus, the derivative there is just going to be 0. And likewise, you'll see that in this pattern of decreasing terms in the denominator, that for each subsequent one, we're differentiating with respect to xk minus 1. It's still going to be 0 because that term just doesn't exist there. So what we have then is a term and then a row of zeros, right? Now, I'm actually going to start computing terms along the diagonal. I'm not going to worry about the terms like here and down, because A, they're ugly, and B, I don't want to spoil this yet. So just hang on. u2, differentiating u2 with respect to xk minus 2. Well, that right there is going to be the same thing as the u1 case, just, minus a couple, or minus a term, really, in the denominator. So what we have, actually, is just nx k minus 2 to the n minus 1 over r to the n minus x1 to the n minus dot, 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 extend the fraction bar, xk minus 3 to the n. And now if we differentiate u3 with respect to x minus 2, well, you'll see that there is no x minus 2 in there. Thus, it is also, kind of overlapping here, but I think you get the point, that it's also 0. And if we actually just continue this pattern all the way down to uk minus 1 and x1, which we can actually just compute real fast, this is like our original substitution, right? So this is just n x1 n minus 1 over r to the n. What you'll see is that there's zeros here. This is actually just a triangular matrix. So whatever the terms are right here that I said I wasn't going to worry about, it doesn't matter, because at the end of the day, we're going to be taking the determinant of all of this, meaning that the only terms that actually matter are the ones along the diagonal. So, and what it is just the product of all the terms along the diagonal, I should specify. So let's find that, shall we? And actually, while computing this, I did realize there was a slight mistake right here. I do apologize. At the end of each of these, there should be an r to the n, by virtue of whenever you factor everything out, at the end of the day, you end up factoring out an r to the n and then an r to the n. So I do apologize. There should be r to the n's in the denominator here. I just noticed that. Anyways, our Jacobian then is just going to be the following. I say the following. Let's actually think about this a little bit. How many terms do we have? Just flat out, how many terms do we have? Well, it's going to be how many we have along our diagonal, and the length of our diagonal is going to be the length of, well, just how big or how long this side is right here, how many columns we have. But I mean, it is a square matrix, so it would be the same as rows. It's square, but you get the point. The answer is just k minus 1. We have k minus rows, you have k minus 1 columns, and you have k minus 1 terms we need to multiply to get the determinant. So doing that, let's just take this term by term. The n right there, it's just going to be an n to the k minus 1, because we're multiplying it by itself, or it's in each term once, and we're multiplying each term, or we're multiplying k minus 1 terms, right? So our Jacobian is just going to be equal to n to the k minus 1. Obviously not just it, we're just starting on it. And then what we'll see is that we have a bunch of terms of like power, right? We have an x to xk minus 1 to the n minus 1, and then we have an xk minus 2 to the n minus 1 all the way down to x1, right? So we can what we can do is exactly just group those together, right? We can say this is x1, x2, ... xk minus 1 to the n minus 1 power. And then what we're going to be dividing by, this is the part where I'm going to be appealing to this right here. We can rewrite this r to the n, x1 to the n, ... We can write each one of those as, well, just a product of these right here. And the reason we can do that is, essentially the following. We said that U1 right here is equal to, this is extremely messy, so I'm using a new color. We said that U1 right there is equal to all of this right here. Meaning that we can set this right here and this right here equal to each other, because at the end of the day, they're both U1. And in doing so, what we find is that the numerators kind of obviously cancel. So xk minus 1 to the n cancels with this right here, albeit, different colors. So what that implies actually, going here, is that r to the n minus x1 to the n minus ... minus xk minus 2 to the n is just equal to, well, that denominator right there, which is just, I'll put the r to the n out to the front. R to the n, 1 minus u2, 1 minus u3, ... 1 minus uk minus 1. Yes, I am right at that. Cool. So what we can do is just replace the denominator of every single term in our Jacobian with something that looks like this. And we can also replace, the next one with, it's parallel. So r to the n minus x1 to the n minus ... and then just xk minus 3 to the n. And this is just r to the n, and that's just 1 minus u3, ... all the way to 1 minus uk minus 1, right? So in doing so, what we find is that, well, first off, we have an r to the n being multiplied by itself k times. So what we actually have in the denominator right here is just an r to the nk. I'm sorry, I do apologize. That it is being multiplied by itself k minus 1 times. I do apologize. And then for each term in the denominator, we have r to the n minus x1 to the n, and so on, multiplied by all that, meaning that we're just multiplying all these terms together, and you'll see that a lot of them are the same. And then after multiplication, what we have then is just a 1 minus u2, but then we have, 2 1 minus u3s. So 1 minus u3, if I can write a u, 1 minus u3 squared, and then we're going to have a 1 minus u4 to the third, and so on and so forth, right? Until we reach, well, 1 minus uk minus 1. And well, let's just look at the pattern here. We have, well, 2, and the power is 1. We have a 3, and the power is 2, meaning that this right here is just going to be a k minus 2. Very rigorous. I know, but this video is going to be long enough as it is. Maybe I'll do, like, a more formal proof with induction later on. But as of now, please take my word for it. So we can just substitute all that in now. We have just, 1 minus u2, 1 minus u3 squared, 1 minus uk minus 1, k to the k minus 2. Actually, if you wanted to be like absolutely evil with this, maybe you could do like some product notation. Oh, that make it look awful. Anyway, I digress. What we can do now then is something we usually do in like, say, Calc 2. And that is just get all of our variables, get all of our x's in terms of, say, u's, right? That's kind of how it would explain it, like if I were TAing. What we want to do now in this case is get all of our x's, so our x1s, x2s, x3s, all of those in terms of u. So it becomes a matter of just finding, well, what on earth is x1 times x2 x times, etc. You get the point. And the answer actually lies in this right here. It's the fact that u1 is equal to, or u whatever, is equal to this x sub something to the n divided by a bunch of u's. So in that very clear way, we can just find what x k minus 1 is, for example. So let's do that real fast. We have x, actually I'll avoid using blue, I'll use like green. So we have x to the k, or sorry, x to the n, pardon me. It's going to be k minus 1. If we just multiply both sides by the denominator, we find that x to k minus 1 to the n is just equal to, well, r to the n time, well, I should write the u up front, u1, and then times, well, 1 minus u2, 1 minus u3, 1 minus u4, and then ... 1 minus uk minus 1. So what we can find then is we can actually solve for xk minus 1, and by raising each side to the power of 1 over n. So what we find is that it's just this to the 1 over n. And then similarly, what we have is, xk minus 2. It's just going to be equal to, well, I'm just going to put the r up front, just as it is, so r, and then, already used r, u2, 1 minus u3, and then 1 minus u4, so on and so forth, 1 minus uk minus 1, all to the 1 over n. And what you'll see here is when we multiply everything together, well, k times, or k minus 1 times, pardon me, is that, because we're multiplying all this down to, x1 as in our Jacobian, what we find then is that this x1 times x2 ... term is just going to be equal to, well, r to the k minus 1 times u1, u2, ... uk minus 1, and then all of these terms right here. But it's going to be very similar to this right here, where it's going to be 1 minus u2 to the 1 times, it's going to be, I'll be frank, it's going to be that right there, right? So what we have then is just 1 minus u2, 1 minus u3, squared, ... 1 minus uk minus 1 to the k minus 2, to the k minus 2. And this is all to the 1 over n power, except for the r, of course. Now, what can we do with this? Well, we can just sub this in, but you'll note that it's not just being raised to, the first power. So this is all being raised actually to the n minus 1 power. So what we have then is a sort of symmetry, but I'll get there in 1 second. I say symmetry, stuff cancels. N to the k minus 1 over r n k minus 1. And then we have our denominator right here. So 1 minus u2 dot 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 1 minus u k minus 1 to the k minus 2. I'm abbreviating that right now just because, well, I don't want to be writing out so many terms. So then what we have is this right here. All of this raised to the n minus 1 power. So I'll actually start with the r. And I suppose I'll kind of combine colors for this part. We have an r to the n minus 1 times k minus 1. And that cancels, just, I'll get to it. Un momento, please. And then for this bit right here, we have, well, all of our u1s raised to the 1 over n power, but then we're raising it to the n minus 1 power, actually. So it's 1 minus 1 over n. So we have u1 dot 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 uk minus 1, all raised to the 1 minus 1 over n. And then we have, well, our denominator right here. We have 1, actually parentheses, really 1 minus u2, 1 minus u3 squared dot dot dot. Or actually, I will just write this as it's written in the denominator. That just makes more sense, emphasizing that they're the same. And all this is raised to the 1 minus 1 over n power. And you'll see here that, well, we have this on top, the 1, and we have that on the bottom, meaning that that cancels with the 1 right there. So it's all raised just to the negative 1 over n power. Now let's just take care of our r's real fast, actually. So n minus 1 times k minus 1 is just the same thing as n times, well, k minus 1, and then minus k minus 1. Nothing, super insane, but you'll just see that these here are the same, actually. So this right here is going to cancel with the n right there. So ultimately in our Jacobian, what we're left with, I'll write this in like our in this color right here, our n to the k minus 1, that term is chillin' until the end, actually. Then we kind of get rid of it. But anyway, is chillin' for now. But then we have an r to the minus k minus 1 right here. And in our numerator, we just have, well, we have the denominator, actually. So then we just have u1 dot 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 uk minus 1. I swear that's k minus 1, all right, please. 1 minus 1 over n, and then we have all of this right here. So we have our 1 minus u2, and then I'll write the dot dot dots. I don't know what I just did. What one note, I swear. 1 minus uk minus 1 to the k minus 2, all to the negative 1 over n. And, ladies and gentlemen, that right there is our Jacobian, and we are not done yet. I'm sorry. Well, not sorry, actually, it's my own video. I love this stuff. But this is our Jacobian, and here's one way to kind of visualize what this is. So what we have right now is j times dx1, dx2, dot, 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 is just equal to du1, du2, and so on. So to actually get our dx's in terms of du's, we need to take the reciprocal of this because, currently this is being multiplied by that. We just need to move it on to the other side. So cross it out, and we just need a 1 over j right here. So 1 over our Jacobian, which is actually what we're going to be using when we evaluate our integral, is just, well, the following. And it actually looks a bit nicer when you write it like this. 1 over j is equal to r to the k minus 1 over n to the k minus 1. And then times u1 dot 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 uk minus 1, 1 over n minus 1, and then times, well, 1 minus u2 dot 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 1 minus uk minus 1 to the k minus 2. all to the 1 over n. So this right here is, 1 over our Jacobian technically, but this is actually what we're going to be using when we evaluate this integral. Speaking of, I think it's about time we do that. Let's do this. So when I actually wrote this out right here, I didn't write it with like an integrand. Like the integrand right here is literally just like a 1. And the reason I did that actually is to emphasize, well, first off for conciseness, honestly, because having this and an integrand is awfully long. But it's also to emphasize the fact that we have, well, how many integrals do we have here? We have k integrals right here, and this is in k dimensions, if that makes sense. Because you'll see here that this right here is 2 dimensions, but it's actually 1 integral, and that's because it's technically a double integral, right? We're evaluating it from 0 to r, and then our bounds for this would just be, say, like the integral from 0 r to the n minus x to the n 1 over n. It would be exactly this right here, actually, just with an argument of 1. To make that 1, you actually have that in 1 less dimension. Anyway, I just wrote that so that way we have k integrals, and that way it's k dimensions. That's actually the reason why I did that. But actually, let's actually evaluate this. Now, in the first step we're actually going to do is, like, just take that part right here. So the part I just talked about why I did, we're going to get rid of that, actually. Yay. So, our integral is just going to be, I suppose I'll write some of the bounds. So it's integral from 0 to r. I'm just going to be writing a dot, dot, dot here, because I think hopefully the pattern is understood now. 0, r to the n minus x1 to the n minus dot, 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 x, and then k minus 2 to the n, all to the 1 over n. And then our actual integrand is just going to be the following. It's just going to be r to the n minus x1 to the n minus dot, 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 minus x k minus 1 to the n, 1 over n. And then we have our dk minus 1, or dxk minus 1, dot, 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 dx1. This is actually our integral. So we can go ahead and substitute everything in. Almost. One thing I want to look at first, well, 2 things actually we need looking first before we sub in our Jacobian. One is this term right here, which actually isn't awful because we've basically already done it, just we haven't known it yet, I guess. Going back to our original transformations, I'm going to clean this up real fast. Kind of erase some circles and lines and stuff, just for the sake of it not looking so messy. You'll see here that we can actually just we can just solve for x k minus 1 and get that in terms of u1, right? So, going down. Where'd it go? Okay. We can just say then that x, this term right here is just u1 times, well, r to the n minus x minus 1 to the n minus dot, 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 x k minus 2 to the n, right? So what we have is just an r to the n minus x1 to the n dot, dot, dot. That's an n. Just trust me, that's an n. Xk minus 2 to the n. And then what we have is, well, a 1 minus u1. But you'll see that we can just continue the pattern as we have before, right? We can say that, x to k minus 2 to the n is equal to u2 times all of that. So at the end of the day, this right here is just going to be equal to r to the n and then 1 minus u1 times 1 minus u2 squared, and then 1 minus, well, I'll write the dot, dot, dots at this point, dot, 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 1 minus uk minus 1 to the k minus 1. Those powers are now the same. So yeah. But yes, okay, moving on. We can define that whole part right there as such, but we also can't really forget about that 1 over n power here. So really, this is all raised to the 1 over n power, meaning that our integrand is just going to be r, and then times 1 minus, well, actually, I should set parentheses. This right here, dot, 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 1 minus u k minus 1 to the k minus 1, and then to the 1 over n. So our whole integral we can express as the following. I'm going to get to the bounds in 1 second. I'm just going to write one integral sign. You'll see why in just 1 second. So we have that, and then we just sub in our Jacobian times, du1, du2, etc. So subbing in our Jacobian, we have, I'm going to put our constants actually just out front straight away. So r to the k minus 1 over n to the k minus 1. And then here we have, well, all of our u's. But I'm going to add those at the end. I'm going to write all these out first. So we have 1 minus u2, 1 minus u2, and then dot, 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 1 minus uk minus 1 to the k minus 2. And this is all to the 1 over n power as well. All to the 1 over n. I do apologize. That's the issue. I'm sorry. There shouldn't be, these should be all be raised to the power of 1. I do apologize because we aren't actually multiplying x1 times x2 times x3 and so on. Yeah, I'm sorry. There isn't any extra power here. That is just as it is. Okay. Makes more sense now. Thank goodness. Okay, and then what we have then here is, well, u1, u2, dot, 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 uk, minus 1. Not exactly the United Kingdom. All of that to 1 over n minus 1. Then we have du, k minus 1, dot, 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 du1. So this is a very long integral. So let's change the bounds, shall we? Because I know that's all what we want to do. Let's just take a look at this real fast, and then we'll do it in general. So in the first case, what we have is our first bound is just r to the n minus x1 to the n minus dot, 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 x k minus 2 to the n. So let's just plug that into u1, because at the end of the day, that's kind of like the integral u1 is, kind of quote-unquote transforming, right? So plugging that in for xk minus 1 to the n, we find, or xk minus 1 really, what's going to happen is that's going to get raised to the n power. So just kind of writing this in here, we have an n over n, meaning that that's just going to, well, cancel, right? So we just have r to the n minus x1 to the n minus dot, 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 xk minus 1 to the n. And you'll see that that's actually just what we have in the denominator. So u1 is just going to range from, well, xk minus 1 being 0, so u1 just being 0, to 1, right? And you'll see here that whenever we plug in each bound for our integral, that it's just going to be 1 every single time. So, coming back down here, it's just an integral from 0 to 1 every single time, and that is one of the reasons why we chose this transformation of coordinates. So it is just a kth dimensional integral. K integrals over the same interval, just 0 to 1. I saw Maths 505 use that notation in a video, so I'm using it. Woo! Shout out to Maths 505. We love them. We love Kamal. Anyway, let's actually evaluate this, shall we? One last time. What you'll see here is that these powers are just the same, the 1 over n's. So we can actually just group this term together as 1, and that right there is just going to be the following. Well, we have 1 minus u1, that part doesn't change. But what's going to change is that we have a 1 minus u2 to the first power, but then times itself. So it's actually just going to be squared, right? So 1 minus u2 squared. And then what we have is the same thing, but for 1 minus u3. And the trend is going to continue up until this term right here, to where we're just going to have dot, 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 all right? We just have 1 minus uk minus 1, and then to the k minus 1 right here. all to the 1 over n. And you'll see at this point that we've consolidated terms, but also that we have a lot of just 1 minus something to a power times u to that to 1 over n minus 1. Meaning that what we can do is just apply the beta function, or I guess quote-unquote invoke it if you want to be like, I don't know, fancy. But we can just do that a bunch, and what we can end up with is actually just an answer and this integral evaluated. So let's do that, shall we? First thing I'm going to do, actually just move this r out to that, so we just have an r to the k. R to the k over n to the k minus 1. Just get that out of the way. And then we have our integral, 0, 1. And the way I'm going to be writing our integral one last time before we actually evaluate it is the following. We have u1 ... uk minus 1 to the 1 over n minus 1. And then we also have the following. We have 1 minus u1 to the 1 over n, right? But then what we have is 1 minus u2 to the 2 over n. And that's going to continue up until 1 minus uk minus 1 to the k minus 1 over n. And this right here is going to result, not quite yet. We have you gotta kind of finish it off. So du k minus 1 du1. Or really, it should be the other way around, but these are all separable anyway, so it doesn't matter an awful lot. But anyway, you'll see that we can just apply the beta function integral a bunch, because we have u to, this right here, and then we have that to that. So let's go ahead and actually just do that. So bring, the r and n down. What we have then is, what's our first term right here? We have gamma of 1 over n, and then gamma of 1 over n plus 1 over gamma of 2 over n plus 1. This is just by the definition of the gamma, or beta function, pardon me. And then that's going to be multiplied because this is, kind of like a separable integral. We just separate it and integrate each part of it with respect to each corresponding u. Meaning that the next one with u2 in it is just going to be gamma of 2 over n. Or actually, for consistency's sake, I'll stick with this right here first. So 1 over n, and then gamma of 2 over n plus 1, divided by gamma of 3 over n plus 1, because we just add those two right there. And you'll see here, actually I'll write one more, then you can kind of see the pattern start to emerge. So we have gamma of 1 over n, and then gamma of 3 over n plus 1 over gamma of 4 over n plus 1, ... And what you'll see here is that these terms start to cancel. That cancels with that, and that cancels with that right there. So at the very end of all of this, what are we left with? If we evaluate the k minus 1th integral, what are we left with? What we're left with is, a gamma of 1 over n still. That part doesn't change. That part's consistent and kind of nice. But what we're left with is a gamma of k minus 1 over n plus 1, and then divided by a gamma of k over n plus 1. And you'll see that, if we were to continue this all the way, that this term is just going to cancel with the previous term that would have been written right there. That term's also going to cancel. And that we're left with 4 terms right here. Three sort of terms, because we have a 1 over, for each integral we have a gamma of 1 over n. So really what we have is a gamma to the k of 1 over n. So then we're left with, 2 other terms, right? So 3 in total, sort of. So we have a gamma of 1 over n plus 1, so gamma of 1 over n plus 1. That part's not awful. Then the denominator, we just have a gamma of k over n plus 1. So bring down this r to the k over n k minus 1 term. We find that this right here r to the k over n k minus 1 term right here. Or I do apologize. That we have k minus 1 integrals. That should be k minus... No! Almost got through it without mistakes. Anyway, sorry. I do apologize. Those should be the same because we have k minus 1 integrals. So we're multiplying gamma of 1 over n, k minus 1 times. I do apologize. You'll see probably why I mix that up in just like 1 second. And one of the properties of the gamma function actually is that x times gamma of x is just equal to gamma of x plus 1. And we can exploit this quite a bit right here, just moving this right here, because after all, that's a 1 over n raised to the k minus 1 power, meaning that this is a 1 over n, gamma of 1 over n, just all raised to the k minus 1 power, meaning that this right here is just gamma k minus 1 of 1 over n plus 1. And as such, we can just combine it with that term right there. So ultimately what this simplifies to is just r to the k, and then times gamma of 1 over n plus 1, but that's just raised to the k power, hence why I kind of mixed that up, over gamma of k over n plus 1. And we're more or less done at this stage. We have everything in terms of gamma functions. If you really wanted to, you could also convert that into factorials as well. So you could say that's 1 over n factorial raised to the k power. You could also do that. It's equally valid. But there is one kind of small thing I did omit throughout all of this. And that's the fact that this integral right here isn't the full Squircle, or Spube, or 10-dimensional Squircle, whatever you might call that. It's a deca Squircle. I don't know. So you'll see that our bounds are from 0 to r, and then from 0 to, well, r to the n minus x1 to the n. So in like two dimensions, what that looks like is, here's the graph of our Squircle. Here's our Squircle. The area we're finding is just this part right here, so we have to multiply it by 4. And in 3 dimensions, the area that we're finding of our Squircle, if I can draw a 3-dimensional Squircle, gosh. The area that we're finding of our Squircle is just this first octant right here still. So whenever we do this in k dimensions, because of symmetry, we actually need to multiply this by a 2 to the k power, just because we're taking kind of smaller and smaller slices of it, if that makes sense. When you go from 2 to 3 dimensions, it makes more sense. 4 dimensions, you can't really visualize it, but here you can at least. So really, there's a 2 to the k out front there, meaning, going down all the way down here, really there is a 2 to the k right here, which is actually sort of cool, because now we have 2r, so the diameter, quote-unquote, of the Squircle, raised to the k power, times this right here, so gamma of 1 over n plus 1 to the k, over gamma of k over n plus 1. This right here is the general volume of a Squircle. The kth dimensional Squircle. I've meant to make this video forever. I am so happy that I actually got it out. But yes, oh my goodness. Thank you all so much for watching if you made it this far. I feel like stickers or something. Yay, you made it to the end. I don't know. A Squircle sticker would be cool. I would buy one at least, but I'll also be talking. Anyway, thank you so much for watching. I hope you enjoyed this whole series on Squircles, and I will see you all in the next one. Thank you again.